Good morning. We will be starting this video by talking about hydrophilic substances and hydrophobic substances. And as their names indicate, hydrophilic substances are substances that love water because hydro means water and philic means compatible with or can do with or loves. So hydrophilic substances are substances that love water. How do they exhibit or show this love of water? Just by dissolving in water. And if a solid substance, for example, dissolves in water, this means that this substance will no more be visible in water. For example, when you dissolve sugar in water, at first you see at the beginning, you see the spoonful of sugar crystals that you put in water. But upon stirring this sugar in water, you will no more see any trace of that sugar in water. The same applies to salt, and the same applies to any substance that is soluble in water. How is this hydrophilic property related to the polar nature of water? Because water is polar, meaning that if we, for example, try to draw the molecule of water, so we will say that we have an oxygen atom here that carries a partial negative charge and two hydrogen atoms that carry partial positive charge. And this is what we call polarity of water. So we have one side of the molecule that is partially negative and two other ends of the molecule that are partially positive. And therefore, any substance that carries a negative charge, whether this negative charge is a true negative charge or this charge is for example, a true negative charge, like the charge on an anion, for example, that has gained an electron or a negative ion, or even if this charge is just a partial negative charge. So any particle that carries those negative charge, whether the partial negative charge or the truly negative charge, will be attracted to the partial positive end of the molecule of water. And similarly, any molecule or particle that carries a positive charge, whether a true positive charge like the one carried by positive ions or cations, or a partial positive charge, will be attracted to the negatively charged end of the water molecule, which is definitely the oxygen side or the oxygen end. Therefore, in order for a substance to be attracted to water, this substance should be charged. For example, if we look here at the sodium chloride molecule, actually the sodium chloride molecule consisted primarily of a sodium ion, a neutral sodium ion, and a neutral sodium atom, and neutral sodium atom, and a neutral chlorine atom. The sodium atom has one electron in its outer shell. So the sodium atom is not in the stable octet state. Similarly, we have the chlorine atom. The chlorine atom has 7 electrons in its outer shell and requires only 1 electron to reach the stable octet state. So there is a simple solution. This single electron in the outer shell will be lost by the sodium atom and will be received by the chlorine atom. So now the sodium atom has 8 electrons in its outer shell, the ones that were in the energy shell below the one that contained the single electron, and the chlorine atom has now filled its outer shell by 8 full electrons. But the sodium atom is no more an atom. It's no more neutral because it lost an electron. So it becomes converted into a sodium ion or a cation, whereas the chloride ion or the chlorine atom is no more a chlorine atom, but it's now a chloride ion, and it is a negative ion. Therefore, it is considered an anion. So sodium chloride is an ionic molecule. It is an ionic compound. Why is it ionic? Because it consists of ions. Why is it a compound? Because it consists of two different elements, sodium and chlorine, but in the ionic state. Sometimes the hydrophilic substance carries a charge, but it's not a true charge like here. Here, the sodium cation carries a true positive charge, and the chloride anion carries a true negative charge. But here, for example, when we look at hydrogen chloride is a covalent compound, meaning that there is neither loss of electrons nor gain of electrons, because the bond between hydrogen and chlorine is a covalent bond in which hydrogen atom shares one electron with the chlorine atom. In this way, hydrogen will have two electrons in its outermost shell, and chlorine, which already has 7 electrons in its outermost shell, will now have 8. Hydrogen chloride is a covalent compound because the bond between H and between hydrogen and chlorine is a covalent bond. It is a single covalent bond, but it is a polar covalent bond. So it is a covalent bond and a covalent compound, therefore, but it is a polar covalent bond. Why is it a polar covalent bond? Because here hydrogen carries a partial positive charge and chloride carries a partial negative charge. And this is due to what? This is due to difference in electronegativity between the hydrogen atom and the chloride atom, the chlorine atom. The chlorine atom has 17 protons in its nucleus, whereas the hydrogen atom has only 1 proton in its nucleus. So hydrogen chloride is a polar covalent compound, and therefore it is a hydrophilic substance. On the next slide, we will see the relationship between carrying a charge, whether true or partial, and being hydrophilic. The third example of hydrophilic substances and charged substances is the hydronium ion. The hydronium ion is nothing but a neutral molecule of water plus a hydrogen ion or a proton, without going into the details of the electronic configuration of the hydronium ion. But the hydronium ion forms when you have a container, for example, that has water, and you add a strong acid to water. So the strong acid is a substance by definition that dissociates to give protons. So the protons of the acid will be added to H2O. So the protons carry a positive charge, water carries a 0 charge, so the overall charge of the hydronium ion is a single positive charge. Because water is polar, it helps dissolution of all these substances that carry charges. And that's why we say that water is an almost universal solvent, because many substances can dissolve in water because of its polar nature. Why do they dissolve in water? Because water is polar on one side and the substances themselves carry charge. And we will see how sodium chloride, being an ionic compound, is capable of dissolving in water, or in other words, how water helps dissolution of sodium chloride, even if sodium chloride is present in the form of a salt crystal, in the form of a crystalline substance. So here you can see the negative particles are the chloride particles of sodium chloride, whereas the positive particles are the purple particles are the sodium cations. And in between them, you have those small molecules that are the water molecules. What happened is that water dispersed the particles. Sodium and chloride originally have a strong electrostatic attraction force between their particles because there is strong attraction between the positive particles of sodium and the negative particles of chloride. But if they stay highly bonded like this, it would never dissolve because dissolution simply means dispersion or distribution of the sodium chlorides, pulling them apart and then distributing them amongst the molecule of water. So what helps them to be dispersed is that we break the bond between them. But if you break the bond between them and do not take any further measure, they will rebind together. That's why the intercalation or the interference of the water molecule in between will prevent their reunion. But how does the water molecule intervene between the sodium particles and the chloride particles to disperse them? Does it occur haphazardly? No, it occurs in a certain order. So as you see, there is a certain logical arrangement. It makes sense. The hydrogen will be towards the chloride. So all the water molecules will be arranged in such a way that the protons or the hydrogen atoms, sorry, not the protons because this is a water molecule, so that the partially, the negatively charged or partially negatively charged hydrogen atoms will be towards the chloride atom. And on the other hand, the partially negative oxygen atoms will be towards the sodium. And if you focus on the diagram to the left where we display the dispersion of sodium chloride between the water molecules, you will always see that the hydrogen atoms are towards chloride, whereas the oxygen atoms are towards hydrogen. So this is what we call dissolution or dispersion of sodium chloride particles. What helped dispersion is hydration. And hydration means addition of water, not only the addition of water, because you might add water and water is incapable of penetrating between the sodium and potassium particles. But hydration here means that the water molecules have intervened between the sodium and chloride so that every chloride particle, every negatively charged chloride particle will be surrounded by water everywhere. And this is what we call hydration shell. Similarly, every sodium ion is surrounded by water molecules. They might be the same water molecules, but at the end of the day, there is a shell of water or a hydration shell that surrounds each of the sodium and chloride particles. On the other hand, we have hydrophobic or water-hating substances. And these are the substances that do not dissolve in water, or in other words, substances that do not mix with water, which means immiscible with water. So immiscible with water means that they do not mix with water. Of course, it's easy to deduce that substances that do not dissolve in water are substances that do not have the charges that allow the water molecules to penetrate in between them. For example, if I have a non-charged or non-charged particles or non-polar molecules, then, and these molecules are close to each other because usually between the molecules of the same substance, we have what we call cohesion forces. Cohesion forces mean that substances are more or less attracted to each other. Furthermore, we have other forces that help the molecules be attracted to each other, which are the van der Waals forces. So in polar molecules, we have cohesion forces mainly. So here, if the substance is non-polar, therefore we wouldn't see the cohesion forces. But if the substances are non-polar, there would be weak attraction forces between them, called van der Waals forces. But if you add water molecules, in order for this block of oil, for example, which is hydrophobic, to disperse in water, to be dispersed in water, the water molecules should interfere and include themselves in between the particles. And this wouldn't be easy because there is nothing to attract the water molecules to intervene between the fat molecules. And therefore, these substances are immiscible with water. And the best example is when you mix oil and water and you find that after a while, the oil being of lower density will flow on the surface of water and will not mix with water. At the beginning, when you shake them, you can see droplets of oil in water, but after they settle for a while, you find that there is a supernatant of oil or a superfluent, a layer of oil that's on the top of water. So we say that they are immiscible with water. This kind of interaction with water is called hydrophobic interaction with water. Actually, it's not hydrophobic interaction with water, it's hydrophobic interaction between the hydrophobic particles that prevents the water molecules from intruding themselves in between such hydrophobic molecules and making them dispersed. So again, the hydrophobic interaction is the interaction between the hydrophobic molecules that prevents them from dissolving in water. It seems as if the oil molecules or the hydrophobic molecules try to coalesce together and go away from the surface of water or minimize their contact surface with water.